Welcome to Complexity Made Simple. My name is Paul Allen, and the subject of today's video newsletter, well, we're going to talk about pairwise comparison today. So just before we get into the video, just a reminder, my 3 books. If you're a green belt, drink tea and read the paper. If you're into statistical process control process control for small batch production, and design of experiments for 21st century engineers. They are all available at lulu.com, and the links are below in the comments. If that's not something that you want to buy, it'd be fantastic if you could support the channel by going to my Buy Me a Coffee page and making a small donation. Just keeps the channel moving, helps to support me with all these videos and materials that I'm making for you. Fantastic. So let's get into pairwise. Now, we're going to just quickly introduce pairwise comparison. And the reason why I wanted to do the little introductory section on this video is just to remind you that normally pairwise comes with component swapping. So normally, if you have a problem with an assembly, you would component swap first, and you would pairwise second. And what does the pairwise do? Ultimately, it finds the root cause for you. Okay, so if you haven't watched the component swap video, the link is in the comments below. Please go watch this first, then watch this. It'll make a lot more sense if you look at the videos in that order. So hopefully now you can go watch the pairwise video. Hope you enjoy it. Okay, so we're going to now step through the process of doing the pairwise comparison. So let's just remind you exactly where we've got to in the process. We've started off with a problem, and the problem was in a complete assembly. And now what we're going to do, we've done the component swapping, and if you remember, we were talking about a computer projector. We split the computer projector into 4. So the bulb and the lens, the power board, the power supply, and the CPU board. So you can see on this diagram here, we've got the item, we split it into 4. We did the component swap with 4 items. We've got the graph down below that's showing us that it is the CPU board that's causing the problem. The problem is on that board, but now we've got several components on that board, and we don't know which one is causing the root cause. But you've gone from 1,000 components using the component swap. Now we're down to a small sub-assembly, and now we're trying to find the root cause. So now with the CPU board, we would go to a pairwise comparison, and that would be the traditional way of going from component swapping to pairwise. But you can also use pairwise on its own. It's got some great techniques. The idea of bob and wow are really good. You can do that with any data set, any historical data set that you've got around you. It's great to take the highest and the lowest output results, clean the noise out of the middle, and leave a nice big signal in your data to do proper analysis. And we'll look at that again in the DOE week. So let me show you now how you proceed with a pairwise comparison. Now we've got a little example that's just specific to pairwise. So we're not suggesting this is the follow-on from the computer projector, but we have a manufacturer of ignition distributors. They're getting a problem, they're fitting them on petrol engines, and they're suffering from vacuum unit rejects. And they've sat down, and this is how pairwise now proceeds. They've sat down with the experts, and they've said, well, which components, which tolerances, what features should affect the vacuum unit rejects. And what they've done is they've identified 10 possible features or dimensions that could affect the result of this product. So they are the angle of the rolled flange, the source of the diaphragm rubber, the hardness of the rollover, the diameter of the unit, the thickness of the rollover, the time pressure at maximum, the time at maximum pressure essentially, the maximum pressure of the press, and the sulfur content of the steel. So they've identified those 8 components. And now here's the way they proceed. Now, just like the component swapping, this is going to be low sample level. Now, in the component swapping, we took 1 bob and we took 1 wow. In this technique, however, what we're going to do is to take 2 bobs and 2 wows. So just the sub-assembly now. So we've identified product that isn't working. We've narrowed it down to the sub-assembly, and we've taken 2 bobs, we've taken the sub-assembly out, we've taken 2 wows, we've taken the sub-assembly out. Okay, and then what we do is for each of them we measure those 8 features. All right, so we get this table of results. Now what I'm going to get you to do, I'm going to get you to do this pairwise in Excel. So it's very easy to do. So one of the things I'm going to ask you to do is to type this data into an Excel spreadsheet so that we can do the analysis. I'm going to show you how to do the analysis of the first one, but then I'm going to ask you to do the analysis of all 8. So at this point, I'm going to stop the video, or if you're watching this on the internet, stop the video and type those results into an Excel spreadsheet. Where you've got the bob and the wow, I've identified those as good ones and bad ones, but really it should say bob and wow. You can also put bob and wow in those cells, and also a good thing to do, for the best of the best, color them in green. For the bad ones, the worst of the worst, color them in red. Type that data into an Excel spreadsheet now. Okay, so we've taken the data and we've moved it now into an Excel spreadsheet. And here is my data in an Excel spreadsheet. You can see, look, I've color coded the bobs and the wows on the left hand side, and we've got the 8 features measured against the 8 sub-assemblies. Now we're just going to do something very, very simple. We're going to take column 1, we're going to take test 1, which is the degrees, and we're just going to sort the whole table using that column. We're going to put that column in order, and we're going to see if it sorts the 2 bobs and the 2 wows into groups. So it's got to be bob and bob, wow and wow, or indeed the other way around. If it doesn't do that, it cannot be linked to our problem, and therefore it is not our red X, it is not our root cause. So let's do that one together. Now, an important thing, you need to highlight the whole table. So you can see I'm highlighting the whole table of data. Then I'm going to the sort function, and I'm going to ask to sort by that column. Sort by column 1, the first column, degrees. Yeah, sort by the degrees column. So in this case, it's got a heading, so it's sort by degrees, smallest to largest. And when I click on that, what happens? Well, you can see in this case that it doesn't sort them into pairs. That's what it has to do. It has to sort them into pairs. A pair of bobs and a pair of wows. If it doesn't do that, it can't be linked to the output. Okay, so test 1 is a fail, and we won't bother collecting any more data on that particular parameter. Now what I want you to do, I want you to go right across the table, sorting by test 2, sorting by test 3, all the way to test 8. Each time you're making a decision. is this variable still part of my assessment, or is this variable going to get discarded? Okay, so I want you to work your way through all 8 columns and make a decision on each one. And then we'll come back, we'll stop the video now, we'll come back and we'll look at the results and we'll move the pairwise on to step 2. Okay, so from that data, you found out, from that initial analysis, you should have found out that test 1 and test 8 failed the test. They didn't sort the bobs and the wows into groups, and therefore there are only now 6 parameters left that we are interested in measuring. And what we're now going to do is go back to production, and we're going to collect 2 more. Another bob and another wow, and we're just going to measure the 6 features. That's the data that's in the red there. Now what I want you to do, I want you to add that data to the data that you've already got. You can see that I've done this in the Excel sheet here, so I've added the data. And now what we're going to do is, starting with test 2, I'll highlight the whole data set again. Starting with test 2, I will sort column 2 first of all. And when I sort column 2, does it create a group of 3 bobs and 3 wows this time? Because that's what we've got to create now. So it's not a 2 by 2 test anymore, it's a 3 by 3 test. Now what I want you to do, put the red data into your Excel spreadsheet and then do the tests on the remaining 6 parameters. And then we'll come back, we'll look at the results, we'll do the next stage of the pairwise. Okay, what you should have discovered now is that there are only 2 tests left, there are only 2 measurements left that interest us. Test 3 and test 5. What do we do now? Well, we do the same thing again. We go and collect another bob and another wow, 1 of each, and we just measure those features. Just the VPN, the hardness, and I'm not sure what and the millimeters. Yeah, so it's a hardness test and it's a millimeters test. And now what we're going to do, we're going to take those 8 data points, and we're going to sort those columns into order. And what we're looking for now is that those sorts create a grouping of 4 bobs versus 4 wows. I'm going to do that on my Excel spreadsheet now. We'll come back and look at the result, and I want you to do the same. Put the blue data into your data sets, and then I want you to highlight the whole group as I've done here, and then we sort by test 3 and test 5, and we see which one of them can sort the groups into 2 groups now of 4 bobs, 4 wows. Do that assessment now. Okay, having done that, I think you'll find that only test 5 can sort them into 4 and 4 green ones and 4 red ones. Therefore, that parameter is the red X. Now this test, this pairwise test, which seems so simple, is highly powerful. You cannot find this out by luck alone. In other words, the test is so difficult to pass, this 4x4 test. It is so difficult to pass. If you've judged test 5 to be the root cause, it's unlikely to be wrong. It's unlikely to be wrong. But here's one thing that we do now at the end of this. We do a confirmation test. So what we now do is we go and find a subassembly with a small dimension. So I think 501 millimeters is the smallest here. So we'll go and find a subassembly with 501 as one of the dimensions. We'll go and find a subassembly with 505 millimeters as one of the dimensions. And then what we'll do is we'll deliberately build those into 3 components that should fail and 3 components that should pass. And this is known as a 6-pack. So we do this at the end of the test. And when we build a 6-pack and we look at the results on a scale, the 3 bobs should be separate to the 3 woes. And if you do a 6-pack test and you separate the results on a scale, so you just represent the results on the scale across the bottom here, so whatever the measure, so remember we were measuring lumens on the projector, for example. So if this was lumens, we would have deliberately built 3 projectors that were guaranteed to fail, 3 projectors that were guaranteed to pass, and that's known as the 6-pack. And if you pass the 6-pack, you found the root cause. But that test, that 4x4 test, the pairwise, is so difficult to pass just by luck, just by the lucky result that you get. It's unlikely that if it's passed the 4x4 pairwise comparison, when you do the confirmation test, it's going to confirm. But the confirmation test is the true test that you found the root cause. And that is pairwise comparison. Okay, I hope you found that little video on pairwise comparison useful. Remember, you're going to use it with component swapping typically. But just to finish this video off, you can use pairwise on its own if you want to. So I know that lots of businesses have these massive databases. So you take all the data from your production machinery, you collect all the quality results, so the product got made, and you've got all these quality results linked to all the settings that you had on your machinery. And you're being promised by the big data analysis people that somehow you're going to be able to do this wonderful data analysis, and you're going to learn something that you haven't been able to learn in the last 20 years of running your plant. Now you can use pairwise in this situation. So instead of just taking all the data and trying to analyze the crap out of 10,000 data points, you can do something a little bit smarter than that, which is a pairwise comparison. And here's what you do. The first thing you do with your data, you sort it in order using this column as the sort function. So what you will end up with once you've sorted it, this row at the top, the whole row, will be the highest result that you saw. This row at the bottom will be the lowest result that you saw. And obviously everything is going to be ranked lowest to highest. Then here's what you do. You carve off the top 20. You carve off the bottom 20. And you get rid of the middle rubbish. Yeah, and what you're then going to do is the pairwise comparison using those 40 data points. Now what are you doing by doing that? Well, you are maximizing the signal in your data. So if there's a genuine link between one of these settings and these results, you've just turned the signal up to the maximum. And now you can do the analysis with this middle bit, of course, is all the noise. So what we've done is we've removed the noise in the middle and we've just left massive amount of signal. So if there's a genuine piece of knowledge to be learned out of that data set, you are going to see it because the signal is at the maximum. Now that's how to use pairwise on its own. But typically, component swap first, pairwise analysis afterwards. These are fantastic techniques popularized by Dory and Shainin. Go use these techniques on your problem solving methodology. And of course, what are you going to do? you're going to make more money.